Welcome to a CSA Global presentation on structural geology. My name is François Landry. I work at ERM, a partner based in Vancouver. ERM is a global consultancy, and we work in the mining sector throughout the life cycle from exploration to closure. We provide services within on the environment field, safety, risk, social, and sustainability. In July 2019, we acquired CSA Global, and we're very happy they're part of our team. With that, I'd like to introduce you to Luke Longridge. He will give us some tips on easy wins and deadly sins in structural geology. If you have questions throughout the talk, please type them in the chat, or there'll be a few moments where you'll be able to come off mute and ask your questions. So with that, I'll pass it on to Luke.
Thank you, Francois. Thanks everyone for taking the time out of your day to join me. I'll be giving this talk on easy wins and deadly sins. The talk is divided into four sections. I'm going to go through some basic principles that I find helpful when thinking about structural geology. Some things that I think you should never do when working with structural data or trying to understand the structure on a project. Some tips on how to collect and organize your data, and then a few easy wins to finish off the presentation. Just a little bit about me. For those of you who haven't met me, I am a structural geologist. I did my PhD at the University of the Witwatersrand, Wits in South Africa, working on Damaran tectonics in Namibia. I then worked in the industry in South Africa, mainly focused on mineral exploration across South Africa and elsewhere in Africa on a variety of different deposit styles. And I've been in Canada almost 3 years now, working with CSA Global. It's been a pretty good experience, and hopefully I will get to meet some of you in person one of these days at a conference similar to this or otherwise. But in the meantime, we'll just take things virtually. So some basic principles. These are not Structural Geology 101, so I'm not going to tell you how to recognize structures or how to measure a fabric in the field. These are just some general tips to think about and to place your structural data collection and your structural analysis in context. Things that I find helpful, and hopefully you will find them helpful too. So the first one is to understand why do we even care about structures? I mean, there's 50 of you out there listening to me, so you must have some interest in them. And so it's always useful when starting for projects or working with structure is to think about why we're doing this. What's the purpose? So obviously the most common one is that structures, when we're working in mineral exploration, may control the mineralization. They may also offset mineralization if they're younger structures, and so we might be trying to find out where our mineralized body has gone to. We also want to figure out which ones are important. There's generally a lot of different structures around. We want to know which ones are important, what are the characteristics of those important ones, and if we do know which ones are important, we want to try and find more of those important ones for mineralization or where other ones are that may have offset our ore body. Another thing that many exploration geologists don't commonly think about in the early stages of a project is that structures are really important for mine safety, and trying to recognize structures early on so that they can be defined can have real implications later on when working on geotechnical aspects of a project. Recognizing these big structures can help prevent slope failures. The other point is that when thinking about structures, these things are often small, narrow and discrete. They can be difficult to see, and they can be difficult to quantify by other means. Sometimes you can recognize them with geophysics, but often they require interpretation. So we care about them because in order to understand them, somebody has to care about them. They don't generally just jump out at you. The second basic principle is that there are three main groups of structures when thinking in terms of mineral systems. And by mineral systems, I mean the broad scale architecture or the requirements needed to create a mineral deposit. Everything from the tectonic events that will trigger and define a temporal window for your mineralization, through to the processes that produce and concentrate fluids along pathways, into trap sites or depositional sites, the processes that cause your metal deposition, and then your post-depositional processes that might allow later detection, exhume the deposit, or preserve it. And so when thinking of that broad mineral system, we want to understand several different types of structures, and we can broadly define those as pre-mineralization structures, things like pre-existing folds or faults, the architecture that exists prior to your mineralizing event. Commonly in mineral exploration, people get caught up a lot with syn mineralization structures, things like fault bends, fault stepovers, or intersections between structures where we're creating space and allowing fluids to move and mineralize. And then very important are your post-mineralization structures, folds and faults that may have affected your mineralization, offset your ore body, or may be important for mining steady slope stability, etc. And for each of these structures, we want to understand sets of structures, their characteristics, their sense of movement. For folds, we want to know their plunge and plunge direction. We want to know where we're sitting on a fold. We want to know what sort of style of folding we're dealing with. And so try and think of your structures in terms of the bigger picture would be the second principle. The third principle is to remember that all structures are a response to a stress field. And so often when you're in the field or looking at structures in Drillcore, you'll see a whole lot of different things, right? And a single event or a single stress field can produce an array of different structures, and it can be quite confusing when you look at them because there's just so many of them. But if you try and always remember that all of these structures are a response to a single event or maybe a few events, but what you're trying to do is relate them back to that system. So a classic example is in a strike-slip system, you can have synthetic and antithetic shearing, normal faulting, thrust faulting, and folding all developing as part of the same system. And your job as a geologist is to look at all the structures and try and understand them in the system. This is why structural geologists are always talking about D1, D2, and D3 kind of events, is because we're always trying to relate each individual structure that we observe back to a single system. My next point is just to bear in mind that the same structure can appear different depending on where or how you're looking at it. A classic example here is the way fold vergence of small scale parasitic folds can change across a larger scale structure. You can get Z folding and S folding on either side of this antiform. And if you've drilled through this, you may never actually see this antiform directly. So you have to interpret that, and so to understand that these differences occur. Another classic example is the way you move from brittle type structures through into the ductile realm in depth, and bearing that in mind, particularly if you're working on a larger scale system, that might be important. Another one is the way that fault zones and their associated damage zones surrounding them can vary in thickness quite a bit depending on where you're looking at them, right? Where you get changes in orientation of faults or stepping of faults, changes in lithologies. The same structure can look quite different. And at the bottom there, I've put an example that I came across quite recently, where we're looking at a structure, and depending on two drill cores quite close to each other, but drilled in different orientations. If you look at the one drill core, this is the same structure. In the one core, it's the drill has gone at a fairly high angle through that structure, and so it appears as a pretty broad damage zone, and fairly easy to identify. In the other drill core, you've got a very narrow, sort of 20 to 40 centimeter wide zone of deformation, and it could be quite easy to miss that little structure. But those two are interpreted as the same structure, and so bear in mind that things might look different depending on how you're looking at them. Another point is that structures are finite. They eventually end, and so classic examples are the relay zones between faults. The faults eventually ends at a fault tip, and you can have a relay zone or a ramp between these faults. Remember that any structure will have a zone where the displacement is the most, and then it moves away to the tip where there is no displacement. Fault propagation folds are another classic example of where a thrust eventually ends. And another example, these are small scale ones, but you can get them on a much bigger scale as well, is non-cylindrical folding. That folds do not continue indefinitely, and eventually your hinge of your fold will disappear into nothing. So when looking for structures, don't keep trying to extend them on forever. Understand that they do come to an end eventually. The next really important principle, and this is the key to putting it all together, kinematic indicators. There are lots of them, and you need to try and understand all of them and how they form in order to piece your system together. We've obviously got the ductile ones like SC fabrics, bending or wrapping of fabrics, object asymmetry, moving through to your more brittle structures such as extensional veins, second fibers, offsets, etc. These are important because they give you the sense of movement, and that's a really important piece to putting together the whole puzzle. And we can use them as long as we've got two planes as a result of one of our kinematic indicators. For example, here, this kind of SC structure, where we can measure those two planes, and using them on a stereonet, we can calculate the absolute transport vector, which will be perpendicular to the intersection lineation between those two planes. Extensional veins, I'll emphasize these. Structural geologists are always looking for them because they often have a particular mineral assemblage associated with them, a vein fill, and so they allow us to associate stress fields, fault kinematics to specific mineral assemblages, and maybe even alteration halos around them. And so, again, we can use them to calculate a transport vector, but we want to know their composition, their texture, cross-cutting relationships, and any alteration associated with them. That's just one kind, but there are many different kinds of kinematic indicators. You've got your ductile ones, like your bending foliation, object asymmetry, FC fabrics, through to your more brittle ones like Lidar shears, thickened fibers, and striations. Any good structural geology textbook should have all of these, and your job in the field is to be able to recognize these and then to place them in context. So pay attention to kinematic indicators is my main point here. And the final point is that it's your job as a geologist to try and put it all together. And this is not always easy. These things don't just jump out at you. It often takes effort to understand a complex system. And you should be trying to think about how each of these structures that you're observing and recording fit into the system while you're collecting data. But at the same time, it might not be possible to understand the whole system until you've completed your data collection. So there's two aspects. The one is collection of data, and the second is in the interpretation. And just remember that different structures may give you different clues and provide different pieces of the puzzle. So just be patient and understand that work is involved in getting to the answer. All right, are there any questions from anyone before I go into the deadly sins?
I don't see any in the chat at the moment, Luke, but
Okay.
individuals are welcome to come off mute if they would like, or if something pops up, feel free to put it in the chat.
Yeah, we'll take more questions later on, so I'll continue for now. So going on to deadly sins. So these are a few things that I've seen over the years, or some of them are attitudes, just things that one should avoid. So the first one, I've seen this a couple of times in my career, is people getting their most junior geologists to do their mapping. So the project manager is sitting in head office, or the VP exploration, they send a field crew out, and the junior geo who's on site all the time, he gets told to go out and do the mapping. I feel that this is often a mistake. Not that these guys are bad geologists, it's just that they may not have the experience to identify all the different rock types that they're going to see. They may not be familiar with the particular style of mineralization on that project. They might not be able to infer structures from subtle features or to identify kinematic markers. So my tip here is to rather send a more experienced geologist or a specialist mapper to go and do your field work. And if you have got the junior geologists, it's a great opportunity for them to join along and to learn. But I find if you get your most junior geo to go do your mapping, the result will never be optimal, and you may miss some important structural features. Second deadly sin is more of an attitude than anything else, and this one is that this deposit is not structurally controlled. So obviously there's certain deposit types which are obviously structurally controlled, things like orogenic gold systems, for example, as we've got over here. But sometimes, particularly when dealing with some magmatic systems, or sometimes sedimentary hosted deposits, for example, roll front or sandstone hosted uranium, there's occasionally an attitude that structures aren't important, that only magmatic processes are important. But I would say that whether you're looking at a small scale or at large scale, there's always some sort of structural involvement. I mean, for example, if you're looking at kimberlites, that may be a classic where you think this is an isolated eruption. How important is structure? But where that eruption occurred is going to be controlled by larger scale, crustal scale structures. So any deposit type has got some structural effect, whether it's younger structures that have cross-cut the mineralization, or whether it's larger scale controls on the whole system. Recognizing the importance of structure is necessary. A third one that I do occasionally see is people not using cross sections, and I would say that cross sections in combination with maps are the foundations for three-dimensional geological understanding ever since William Smith's map of 1815. And I believe that as you're working on a deposit and trying to figure it out, you should be constantly drawing and redrawing cross sections. You should almost have a portfolio of them. And that's even if you've got some of the newer software like Leapfrog, which makes three-dimensional modeling very easy. Hand-drawn sections are important for just testing out ideas and thinking about your geology. And I believe you should be drawing multiple sections and correlating multiple attributes across them. You shouldn't just be doing your lithology. You should be correlating grade, structures, and alteration across different sections. Stereonets. So I find you often get two kinds of people when speaking to people who are not structural geologists. Those who give you the reaction on the left, who kind of are terrified of stereonets, and then sometimes when I'm talking about them, you get the dog on the right, and people just fall straight asleep. And I guess stereonets can be messy, but then so can geochemical data. And you wouldn't take a full acid digest ICP data set and expect to understand it immediately. It takes analysis, and there's ways to do this. To tease your answers from the data, you wouldn't just plot your stereonet like I've got on the top right there. You need to break it down. Domaining, classification, there are tools to understanding your structural data. But if you shy away from using stereonets, you won't have much chance. They are a fundamental tool. And if you ever want to learn more, or you find you struggled with them, then feel free to reach out to me. Another sin that I have occasionally come across is people using unsubstantiated geological models. And when I talk about geological models, I am referring both to three-dimensional geological models that people typically use Leapfrog for, as well as to referring to sort of hypothetical models of mineralization. And so it's critical to make sure your model is backed up by data and is testable. And it's useful to think about the scientific method here. Hypothesize or design a model or create a model, and then test it. Geological models are always wrong. They're hypothetical constructs. We're trying to make them less wrong. And the only way we can do this is by testing them. And by testing them, I don't mean looking for evidence that supports them. You've got to be very careful of confirmation bias in geology. I'm talking about thinking of ways to prove them wrong and then going to test them like that. And it's also useful to think about the fact that any geological model should be based on data collection, which should be separated from data analysis, and the combination of those two things should provide your evidence for your model. So beware of unsubstantiated geological models that haven't been tested. There's a place for hypotheses, but if you can't test them, they're no good. And the next one that I've got here seems fairly obvious, but I have seen where people just do not collect any structural data. So I'm not saying that you need to go and draw oriented core on every single project, but I'm saying that when you see a drill core like we've got over here, and there's an obvious zone of deformation running through, that you should recognize that and log it into your database. Any shear zones, fault gauge, gouge, lithological contacts are also an important structure. And the other point is that logging is only one type of data collection. Mapping is another kind. But taking note of cross-cutting relationships is an important piece, right? So this image on the right here is a nice example. We're not necessarily having to measure any of these structures, but recording somewhere, whether it's in a report or a presentation, different cross-cutting relationships. So we can see that we've got a mineralized vein here with sulfides along the center, and that is cross-cut by these younger carbonate veins, which are themselves cut by these very fine structures that you can almost hardly see the structure, you see the offset. So collect that information, record it, so that you've got it, and so that you're starting to understand cross-cutting relationships and timing relationships. Again, do we have any more questions before I move on to the next section on collecting and organizing your data?
None in the chat, Luke.
Okay, I'll move along then. Okay, so I'm going to be focusing mostly on collecting and organizing data from Drillcore, but the principles here, some of them will apply to collecting data in the field as well, although Drillcore has got its own intricacies, which is why we focus on some of the aspects of that. So the first real important point to note when collecting data from Drillcore, or structural data, is that there are several steps involved. The first step is actually doing the drilling and orienting the drill core. And that's closely related to the second step, which is marking up the core. And by that, I mean applying an orientation mark to your drill core once it comes out from the drillers and onto the core trays. So these two steps need to be done accurately, and even small errors in your orientation and in your markup, combined with potential inaccuracies in measuring of your structures, can result in significant errors that can affect the quality of your results, right? So if you have 5-degree error in your orientation, you don't do your markup accurately and you get a 5-degree error there, and then you only measure to within 5 degrees on your structures, you've got a 15-degree error, which is quite a lot. And when collecting data from Drillcore, you want to focus on doing each step properly and clearly. And these two first steps are critical. If those aren't done correctly and accurately, it's impossible to fix it after the fact. So with Drillcore Orientation, we should really be using one of the several good electronic core orientation tools available. The days of using spear points or pencils for Drillcore Orientation are over. Most drillers will have a preferred tool that they use, and that's okay. But the main point here is that the drillers should be closely supervised. So the geologist who's charged with overseeing the oriented program should make sure that they understand which orientation tool the drillers are using, and should be spending time at the rig watching what the drillers are doing and making sure that the orientation is done correctly. And core markup is basically a part of this process. So this is your first chance to correct any errors. So you have an opportunity here to correct errors with the drillers before they become systematic. So you want to be doing your core markup as soon as possible when that core comes out of the barrel, so you can flag any issues and raise them with the driller immediately. And at this time is also an opportunity to apply an orientation confidence attribute to each core interval. And what we mean here is that each run, you'll have an orientation line on a run, and then the second run, hopefully your orientation line, your core fits together and your orientation line lines up. And when those line up, you know that you're fairly confident that your core is correctly oriented, and so you can give it a level 1 confidence, and then you might give it a level 2. Sometimes you could come up with another level as well if you're really not confident at all. But this is where you might have slight offsets between your orientation lines, or maybe you've got an interval of core where the core is quite broken and it's very difficult to piece all the drill core together. All the pieces aren't lining up really well, and so here you could put a lower confidence attribute. And this just allows us later on, when we're working with the data, to filter out lower confidence data and to see what a difference that core orientation makes to the end result. So pay attention to your core markup. The next principle for collecting structural data is to take the time to set your database up. So what we're trying to do here is to make sure that the geologist can focus on observation, while at the same time making that data that they're recording queryable. And to make data queryable, you want to have set up specific fields for each structural data type and each value, right? All your different fault folds should have their own code. Your shear types should have their own code. You should have codes for alteration. You should have codes for mineral fill. You should have codes for shear sense. And the point is that these codes should be standardized, and they should be tailored to your specific project or to your company database. Then when the geologist is doing the logging, they don't have to fill out every value, but they can complete the observations that they've made. And if you do this correctly, you should have little or no information in the comments column. Very often things that are difficult or complicated get buried in the comments column, and there can be really important information in there, but we're trying to move that information out of the comments column into specific fields that we can query. That means then when you've got the orientation of a particular structure, you can query it by its fill or its alteration or its shear sense. And so it becomes much more useful. Then when you're logging the core and you're going through a and looking at your structures, you should try and identify marker structures. This is not always possible, but on many projects you might have a cleavage, a fabric, or a bedding, or particular vein set, something that you expect to be fairly consistent throughout the project site. And then when you're going down your hole, think about the orientation of the hole. So you can see that this guy on the right here is looking at his drill core. He's trying to orient the core and thinking about the structures that he's measuring in the context of that oriented hole. And then as you go down the core, you keep doing this. And so if you observe any significant changes in dip or dip direction of that marker structure, then you can check and see, is there a problem with the orientation of the core? Make a note of that. Or have we moved through a fault or gone around the axis of a fold? And does that mean something? So by paying attention and not just logging blindly, you can do an extra sort of quality check on your oriented structures. And then next point is on relative timing. So geologists are pretty good at recognizing cross-cutting relationships and timing relationships, but in drill logs, these can be really difficult to capture. And there's a way to do this, and the way is for each structure that you measure to give it a unique identifier based on the geologist's initials and on the date that was logged. So you can see these IDs down here in the bottom left. And then you can put a cross-cutting relationship column in there, and you can say that that structure is cross-cuts the earlier structure or is coeval with a different structure. This allows you to group structures not just by alteration or vein fill, etc., but by temporal relationship as well. So this is a useful one. I've seen a few projects where we have hundreds or thousands of measurements, 100 measurements in a drill core, you know, and that's a real waste of a geologist's time, actually. So you don't need to take a measurement of every single structure. What you want is a representative data set. So you want to identify structures with a similar orientation or a similar character, and this is especially if you're dealing with things like jointing or foliation or bedding, where you've got lots of the same kind of thing, or little veins. So you want an estimate of the frequency of that structure type. Like, for example, you could have how many veins per meter or how many veins per 5 meters, depending on what you want. So that vein multiplier needs to be quantified for the project. And then you take a representative measurement and you add a vein multiplier or quantifier to give you a sense of how many of that structure there are. That allows you to still get a weighted sort of statistical analysis of which structures are more abundant than others, without having to spend the time trying to measure every single structure, because I guarantee you it's almost impossible to measure every little tiny structural fracture. So it's much better to try and just collect representative data. And again, here, pay attention to shear sense. So when you can see kinematic indicator, record it. And if you can, if you saw this in Drillcore and you saw these two orientations, you would record them, and then you would use a Stereonet to work out the the movement direction, and you would record that movement direction. So it might take a little bit of time while you're logging the core to stop and say, okay, I've measured these two structures. What is the movement direction? Let me work it out and let me record it. So you need to take the time to record these things because shear sense is really important. And then once you've collected your structural data, it is possible. I said at the beginning that once you've done your orientation and your core markup, it's really almost impossible to go back and fix errors there. But what you can do is recognize errors and filter it from your data set. And the way we do this is by looking for core spin. So we try and validate the oriented hole data by drill hole, or sometimes by, if you've got a whole bunch of drill holes with consistent orientations, you can do them by set. But basically, you plot a single structure that you expect to have a relatively consistent orientation, such as your cleavage, foliation, vein sets, or bedding. And then, so we've done this for a single drill hole here, and that's the plunge and azimuth of the drill hole. And what you can see is that the poles to the planes for these marker structures plot in a circle around that core axis. And so what this means is that the orientation line has been moving around the core axis. So the drillers haven't been orienting correctly. And so that means this is what we call core spin. And so you want to just recognize data that has got core spin. So is it for the whole drill hole, or is it only for certain intervals in the drill hole? Is it just that one drill hole, or is the whole program affected? You can start to filter this data in. And this is an important step to checking or validating your data before we do any structural analysis. Because if you do bring this poorly oriented data and try and do an analysis with it, you're going to get really confused because it's really messy. So that's a tip for working with the data once you've collected it. So just to sum up here, when we're looking at structural data quality from oriented drill core, we can assess it during the core markup stage, where we have procedures for matching orientation marks, applying orientation line confidence, and identifying problems and communicating them, or fixing them with the drillers. Secondly, when we're doing our measurements, we want to measure as accurately as possible, and being aware of orientation of key structures and whether these key structures change relative to the drill core. And then finally, once you've collected the data, when you're starting your analysis, to check that data from each hole for indications of core spin. Right, let me go through and finish off with a few easy wins. So some of these might seem fairly obvious, but I still think they're useful to emphasize. So the first ones, yeah, seems really obvious, is log structures and correlate them. So what I mean here is by trying to treat each structure as an individual lithology. Right, so not just saying fault, 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 shear, shear, shear. Right, trying as you build up a data set of different cores in different places, trying to link those structures together and then treat them as a specific structure. So that is fault one. That is the shear with the chloritic alteration, whereas that's the shear with bleaching associated with it or something, right? So trying to characterize them a little bit more than just saying that that's a fault. And so this doesn't have to be an oriented core. This can be an oriented core as well. Second tip, so this is going away from the core. I see a lot of people are collecting LiDAR data nowadays, often with orthophotos, and it's been my experience on a few projects that really good elevation data, there can be a wealth of hidden information there. And so this can allow you to do a basic structural assessment before you've even gone into the field, allow you to ask some questions about things before you get a chance to go and drill, formulate some hypotheses to test, for example. So here's an example that I worked on a couple of years ago, just a very basic structural interpretation that you could see on the LiDAR data, which helped to inform a subsurface geological model. And just to compare, so this is the LiDAR data that you see, and if we put the SRTM data on top, that's what we've got, right? So you can see how much information is sitting in that LiDAR data, and I find a lot of people don't use it and don't interpret it. So LiDAR is really useful for structure. If you've got it, use it. On a related note, use your geophysics. Lots of companies are almost routinely collecting airborne mag and IP data in the early stages of projects, but they often only carry out a rudimentary interpretation. This sometimes is carried out by the actual geophysical survey company. But, you know, the value of that geophysical data is in the interpretation, not in the data, right? You're trying to find something out from that data. You're trying to observe what's going on under the ground. So try to do that interpretation and then use the interpretation to pose questions similar to the LiDAR. So you want to say, oh, I think this structure is offsetting that structure. What are these two structures? Let me go into the field and make some observations and test that. So take that data that you've got and use it is the other easy one. Another easy one is that a few good measurements are much more valuable than lots and lots of bad measurements, okay? And it only takes a few high quality structural observations to recognize common characteristics, and sometimes you only need a few good outcrops where you might just be able to observe important relationships. And where you do get those good outcrops, then spend the time to make consistent observations, characterize everything that you see, and you can, in a single outcrop, take loads and loads of measurements, recording mineral association, sense of movement, textures, etc., etc. So quality over quantity is another really easy win. We're all limited on time, and so rather than trying to collect everything, just try and focus on the important stuff. Another easy win tip is again relating to logging, and I find when you're logging, you're collecting data. So if you split up the tasks, you're more likely to do each well. So when you're logging core, do you generally either try and log your structure alteration, lithology, etc. as you go down the drill core all in one go, or do you break each type of logging up into a separate task and go log lithologies first and then relog the whole for alteration, then relog the whole for mineralization, etc. My advice is to try it. It might be a little bit more time consuming, but I think it really helps to make sure each job is done well, is to break up your logging into specific tasks. And particularly, structure is only one aspect, but for each other type of thing that you're looking at, it just helps you to be a bit more focused on the task at hand. Someone asked a question about RQD data, and this is an easy one, right? have seen a lot of companies do collect it routinely, but I've seen several projects where it isn't routinely collected. This is something that you can train your laborers or your technicians to do when they're marking up the core, and having this data available can help you to recognize things, so faults where you've got continuous zones of low RQD. So this is an example that I was working on recently. We were trying to map out some structures for a project for a geotechnical analysis, and I was looking at the RQD data, and you can see, like, hang on, there's these zones of low RQD that kind of line up, and then we went back and looked at the core photos, and sure enough, you can clearly see that there's a fault running through there that hadn't been recognized previously. So that RQD data is useful, so do collect it. Next, this is a bit more on the analysis side, and particularly you can do this in Leapfrog really easily, but spatial domaining is foundational to structural analysis. So whether you're doing this in 3D or whether you're mapping an area and collecting structural data in the field, you want to be creating spatial domains. So areas where you think structures are similar, and then analyzing your structures in that area as a whole, rather than trying to cover your entire deposit or your entire field area in a single go, because structures do change and move and vary, and so trying to create smaller spatial domains is a really useful tip. And you can also do inverted spatial domaining in Leapfrog, where you plot your data on a stereonet, and then you can look at where things cluster and say, oh, let's look at this data relative to that data, and start to see where your different structural clusters fit spatially. This relates back a bit to the RQD data, and something that I think a lot of companies are taking core photos, but just make sure you do a thorough job of it. I cannot overemphasize the usefulness of good core photos to structural analysis after the fact, right? I'm a structural consultant, and there is an enormous amount of work that I can do using core photos, which saves people having to fly me to the other side of the world and haul out drill core and log structures, right? You can do a heck of a lot. And so when I say take proper core photos, I don't mean just take a photo of the core box like that. I mean, they should be high resolution so that you can really zoom in and observe the structures close up. You should be taking the photos of the core wet and dry. Some projects I see them take photos of the core cut and uncut, which is quite useful as well. If you do take photos of the core once it's been cut, make sure that it's been washed off so you don't have any dust residue on the core, so that it's nice and clean. Make sure you crop each photo nicely. Spend the time to crop the photo down with the core box labeled, and you've got the drill core labeled, and then it's really useful to have each photo labeled, so not like you've got on the left where it comes off your digital camera, you've just got your image number, but actually relabel the photo with the whole number, which box it is, whether it's dry or wet, and the from to. Makes it really easy to go back and inspect things after the fact when you're trying to do an interpretation and you're not sure. Rather than having to dig through core boxes, you can just go back and look at the photos. So that's a really easy win, and something that I think people should really pay more attention to. Another useful, easy win is working out stratigraphy. And so early on in a project, you'll often be logging lithologies, and people tend to be splitters at this stage. And by that, I mean, they break the core down into lots and lots of tiny little pieces. But after a while, you want to go through and start working out which pieces go together. Are there sedimentary sequences which can be grouped and are consistent? Are there any marker structures that you can recognize? And the reason I emphasize this is that these marker units or groups of units can be critically important to understanding structure. They can show you where you've got offsets. They can show you in sedimentary systems how your basin might be developing. But they don't have to always be. By stratigraphy, I'm not always referring to sediments. We also get a magmatic stratigraphy very often, and so it's important to try and work out this and use it to create some order out of your lithological chaos. So, and again, stratigraphy can be an important control in mineralization. So another reason to spend the time. So in the early stages of a project, sometimes you might not know your stratigraphy. And so you might just be logging your cores for lithologies. But once you've figured out the stratigraphy, you want to go back to those cores and log as a separate category. So separate from your lithology or alteration or mineralization, you want to come up with stratigraphic log. And I found this extremely useful on projects to have that, to have taken the time to work out stratigraphy. And then the next one that I've got here, just a final point, is to use multiple different models and to test them. So this is about not getting too dogmatic about your ideas, about how you think a deposit formed or how you think your deposit looks, and this applies both to targeting or conceptual models of ore body formation, as well as to three-dimensional geological models. Come up with alternatives and go out and test them, and think of ways that you can test that. Often you've got an idea and you've got a drill rig. Try and move away from just punching another hole to try and extend your mineralization. Obviously you want to do that, but try and use your drilling to test your ideas and say, oh, what happens if I drill over here? I should intersect that structure. And then if you don't, then you know that your interpretation is wrong. And so you've consciously trying to test your ideas and verify your models. Right, so that's all from me for today. I hope you all got something useful out of my talk. We do have a more comprehensive principles of structural data collection and controls one-day course that CSA Global offers. If you're interested in that, please register your interest. I'll just thank you all again for listening to me, and I hope that you enjoy the rest of your afternoon wherever you are, or evening. I guess there's people all over the world. Excellent. Thanks so much, guys.